Okay, welcome back. So this will be our last example that we work through together on the Taylor and maclaurin series guided notes. So let's dive right in. Let me grab my magic pen here. Find the Taylor series for f of x at x equals 2, and f of x is going to be the quantity x over 3 minus x. And you see I've rewritten that over here. I have a little note to self that we're going to check Wolfram alpha to check our answer when we're all done doing this by hand. So let's go for the 0th order Taylor polynomial. So I'm just going to rewrite the function, which is x over 3 minus x, and then remind myself that I need the function evaluated at 2, see, because x is 2. So that's obviously, if you store 2 in here to that expression, you can see you're going to get out 2. So then, note to self, our 0th order polynomial is going to be 2. Now let's go for our first order. Now we know we're going to need the derivative. I can tell you, use the quotient rule. So bottom times the derivative of the top, which is 1, minus top guy, times the derivative of the bottom is negative 1, over bottom squared. Well, when you do that, okay, let's clean that up on the next slide. When you do that, you know, the top's going to clean up 3 minus x plus x over 3 minus x whole thing squared. And this is going to cancel with this, and basically you're just going to be left with 3 over 3 minus x whole thing squared. Okay, so that's our derivative. But remember that we need to store 2 in there. So f prime evaluated at 2. So if you store 2 in there, obviously you're going to get out 3, right? So now you're ready to write your first order polynomial. So that's going to be 2 plus 3 times x minus 2. And so now you're so used to this sort of robotic process. Okay, now let's go to the next slide and get our n equals 2 and go for our second derivative. Now, what you can do is you can take this first derivative and rewrite that as 3 times the quantity 3 minus x whole thing squared. So let me just write that above here. The first derivative is 3 times the quantity 3 minus x. I should say whole thing. Here, I wrote it, my pen was being fussy, sorry about that. I wrote it off to the side here. The first derivative, I'm going to rewrite it as 3 times 3 minus x whole thing to the negative 2. So then when I go to get the second derivative, okay, and I'll do this in another color. Here, I'll pick purple. Remember, I'm going to take negative 2 and multiply it times 3. So clearly I'm going to get negative 6 times 3 minus x whole thing to the negative 3. But then chain rule, don't forget about chain rule. So times negative 1. So basically this negative 6 times this negative 1, you're going to get out 6 on top. So 6 over 3 minus x whole thing cubed is a different way to write that for the second derivative. Okay, so once we have that second derivative, we can evaluate that. So then we're looking for the second derivative evaluated at 2. Well, obviously you're going to get out 6. Okay, so then we can write, you know, piece of 2x, the second order polynomial. I just want to reiterate that, you know, we have to feed off of what we did with p sub 1. So here's p sub 1x, 2 plus 3 times the quantity x minus 2, and just, you know, build off of that. So then p sub 2x is going to be 2 plus 3 times the quantity x minus 2, and then I like to use that factorial notation. So plus 6 over 2 factorial, and then x minus 2 whole thing squared. I'm kind of running out of room there. So, but, you know, clearly 6 over 2 factorial is going to clean up. It's going to be 3. So we could even, let's rewrite. So second order polynomial then will be 2 plus 3 times x minus 2 plus, that's going to clean to be 3. So 3 times x minus 2, whole thing squared. Then on the next slide we can go for the third order. And so on and so forth. So I'll lead you to verify then that the third order, or the third derivative, is going to be 18 over 3 minus x, whole thing to the 4th power. And therefore the third derivative evaluated at 2 is just going to lead us to 18. So then we start to, we're trying to get that nice pattern recognition. So our third order polynomial then is going to look like 2 plus 3 times x minus 2 plus 3 times x minus 2 whole thing squared, and then plus, now the thing is, it would be 18 over 3 factorial, but 3 factorial is 6, and 18 over 6 is right back to 3, so you're starting to have some pattern recognition there. So plus 3 times x minus 2 whole thing cubed. So you're starting to feel like p sub n is basically 2 plus, and you're noticing all, so you're kind of looking here for your pattern recognition. They all have 3's, and then like the first term is raised to the 1st power, the second term, 2nd power, etc., etc. So you're feeling like they all have 3's. So let's throw in the summation there. Summation n going from 1 to infinity of 3 times x minus 2 to the n. So I always say just, feel if that's right. So, if you put a 1 in there, you're going to get out this first expression. And if you put a 2 in there, you're definitely going to get out this second expression. Put a 3 in for n, you're going to get out this third expression here. And the constant we're just letting float out. So final expression there, we can indeed express the Taylor series as, I'm going to call that capital T, but we can call that 2 plus summation n going from 1 to infinity of 3 times x minus 2 to the n. So it's constantly that pattern recognition. And now the fun part. I'm going to hit pause as I pull up my live cam. I'm using my iPad here to record this. I'll pull up the live cam feature to show you my computer at home in Wolfram Alpha. So I'm really excited to use this feature of, I'm using Stage Pro to record this. So you can see our answer is still in purple there written. This is my, my home computer, and I typed in find the Taylor series for, and then notice how that, Wolfram Alpha asks you what function to expand and the expansion point, and I wrote x over 3 minus x and 2. And what's really neat, you're actually going to see me, which I'll try to hold the camera steady here as I do this. I'm going to page down, and voila, it says series interpretation. It gives you at x equals 2, and it tells you 3 times negative 2 plus x to the n, and then plus 2. So that's indeed what we got. So many things there you can do to check your answer. Hope that helps. Okay, so I just wanted to reiterate, we found our final answer right here. Now I'm going to go and read our final example together on the guided notes, which already has a solution. I just wanted to talk about something with you. Okay, and last but not least, for your nighttime reading and viewing pleasure, this won't be on the final, but I wanted to mention it just in case. Just in case you're moving on to future levels of calculus. So Taylor's formula. Just a quick mention here that you can show that a Taylor series for a particular function converges for every value of x using Taylor's formula. So I just wanted you to have that in your toolkit as you head on to Calculus 3 and Real Analysis and all those wonderful courses. The big thing is it kind of, if you've taken proof by induction, if you know what proof by induction is, you're looking for R sub n, and I like to think of it as once you've noticed what the nth term is in your Taylor expansion, you can take a look at the n plus first term. So we're going to designate R sub n as basically the n plus first term. And if you can show, this is big right here, that if R sub n goes to 0 as n goes to infinity for all x belonging to I, we say that the Taylor series generated by f at x equals a converges to f on that interval. And we write that f of x is this. And so I left you with this lovely nugget of thought here. Let me scoot this down. Erase all my writing there. This proof is taken from Thomas's calculus, and we show that the Taylor series for cos x at x equals 0 converges to cos x for every value of x. And I just want you to, I like to think of it as sort of the inductive step. Once you get that pattern recognition and you realize what the nth term looks like, then the next term would be like the n plus first term, or here we're using k's instead of n's, or the k plus first term. And if you can show that that this remaining term goes to 0 as k goes to infinity, you can say that the series converges to cos x for every value of x. So I just wanted you to be able to read through that and just have one deeper nugget of understanding as you head off into maybe theoretical calculus. So good luck out there, and if you ever have any questions, feel free to email me. And that concludes our notes for Taylor and Maclaurin series. In the future, I hope to add more and more videos to my iTunes collection. Good luck, everyone.